I'm going to just give you some basic feedback on the practical because it might be useful to you. So the practical was about X-ray diffraction, and can somebody tell me how the X-rays are generated? Because, one of the important things in writing up a practical report is that you put enough information to allow the work to be reproduced by somebody else in another laboratory. So how are the X-rays actually generated? Any ideas? That wasn't a part of the practical question, but I just wondered if you know how X-rays are generated.
Radiating material?
It's not actually radioactive material because probably we are not allowed to use it. Okay.
Some wavelengths reflected.
Yeah, I mean we are generating specific wavelength, right?
Well, there was electron bombardment on a metallic object.
Correct. So we throw a stream of electrons at a target, and do you remember what the target is?
The copper or something. Was it copper something?
Copper. It was copper. So within the copper, the bombardment by electrons causes transitions between specific energy levels, and that is the reason why you get a specific wavelength from the copper. Okay? But the intensity depends on the accelerating voltage, how much energy the electrons have to hit the target. Okay? So that is important. Can you remember what the accelerating voltage was?
20 or 30.
Yeah, kilovolts. So that's the range according to surname. Okay? According to your surname. So it's important to mention that the accelerating voltage was, there was a switch on the machine, 20 or 30 kilovolts, because that determines the intensity of your peak. Okay? So the first thing that you might mention is in anything you write which is published as a part of your research, it's got to be reproducible, otherwise it's not science, okay? So the first thing is that the accelerating voltage then there is the wavelength, which was from copper, and the wavelength was I'm just putting this down from memory, okay? Now, there was also copper K beta, but we are going to ignore that. It basically gives you a broadening of the peak because we are not filtering it out, okay? It's a lower intensity emission. Okay, then you are measuring intensity at particular values of 2 theta. Okay? So, what are the units of 2 theta? Can you recall? Degrees or radians, but in our case the machine was calibrated clearly in degrees because it went up to 180 degrees on this side and another 180 on that side. Okay? So very important to mention that. I mean, it would be kind of obvious from the size, the magnitude of your degrees, like, if it's 90 degrees, it's not going to be 90 radians because that would be really going around in a circle several times. Okay? Because 2 pi radians is the maximum. So pick up your script according to your surnames.
Yeah? Yes.
According to your surnames. Script.
yes. What is this? What's this?
Which class are you in?
Yeah, Alibag. Allah.
What is your surname?
Anand.
A. Is all that. Excellent. Okay, so we've got these parameters listed. What else should we have? How does the intensity depend on how long you count for? Yeah, obviously we need to. Yeah, we need to state the time period over which you collected the information at a particular value of theta. Now, what was the difference between pick up according to your surname? Okay. What were the two kinds of specimens that we used? Come on, guys.
High fluoride environment.
Okay, and what was the crucial difference apart from their chemical compositions?
The crystal structure are different.
One was it?
One is cubic,
And what else? That's absolutely right, but what else was the difference between the two?
One is single crystal, the other is
Excellent. So we had lithium fluoride, single crystal, okay, so that's quite important. With its edge parallel to 100 vertical, and then barium titanate polycrystal, because it's basically a powder that's been compacted into a sample. Okay? Now, when you make your plots, it's incredibly important that you actually label the plots, correct? So, typically you had intensity in perhaps counts per, let's say, 20 seconds or whatever it was, okay? Versus 2 theta, and you might get a curve which looks like this. So both of these should be labeled with the units. According to your surname. That's your raw experimental data, and if you don't put the units down, then nobody can follow what you've done. Okay, so that's the basic information that would be necessary to reproduce the work. Okay, there's nothing more than that you need in order to completely reproduce the experiment in another laboratory. Okay? Everyone happy with that?
Yeah.
Did you have a question?
What is the output, by the way?
I'm hearing
What's the thing out of how many marks?
oh, 30. It's 30% of the total mark of the exam, of the. Okay. But you have no questions about this, right? Okay. Okay. Now, there's a couple of really interesting questions that were asked of you inside the practical handout. And one of them was you had two peaks from the lithium fluoride, right? And they represented the 200 and 400 planes diffracting. Okay. That is something that you had been told in the practical handout. And you had to work out the lattice parameter from each peak. So lithium fluoride. From 200 and 400 planes of the cubic crystal. No, you please. If you have a query, just ask. Yeah. So you had to work out the lattice parameters from this, and I wasn't really. We didn't mark you down for making some sort of a mistake in working out the lattice parameter, but you had to explain why the parameters are different between these two peaks. So you might have found a small difference in the lattice parameter from the 200 peak and the 400 peak, not exactly identical. And I would be very surprised if they came out exactly identical. Okay? So according to your surname, right? You can pick your script according to your surname. Now, if you go back to when I introduced X-ray diffraction, not a single one of you remembered that a more accurate lattice parameter comes from a larger angle theta. Can anybody remember why? So, more accurate lattice parameter. So you'll find this, if you review the lecture on, what is it called? Where are the videos located? QM+, yeah. Then the sine function is shaped like this, isn't it? Okay?
Yeah.
So sine theta varies sharply with theta at small theta. So the likelihood of error is greater when the variation, when sine theta is very sensitive to theta, and the likelihood of error is small when sine theta doesn't vary a lot with theta. It's simple as that. And that's why the value that you get from a large Bragg angle is always going to be more accurate than from a small Bragg angle. Okay, is everyone happy with that? It's according to alphabetical order. Yeah. Okay. So that's a really interesting question, which was taught to you in the lectures, and if you look in the slide presentations, you'll see it there as well. Because there will always be errors in measuring theta, etc., and the sine of theta will be more sensitive to theta at small theta. The second point was that when you looked at the peak for So barium titanate. It was not just broad, right? But it was also asymmetric. I've kind of exaggerated it here. And what the question was, what is the reason for this asymmetry? Bearing in mind that barium titanate, what you said earlier, yeah, is tetragonal. Yeah. So what is the reason for the asymmetry? You were told that there will be 101 and 110 peaks.
It has, it's meant to have 2 peaks, that's very good.
Very good, very good. So even though you were using your mobile phone, you were paying attention, okay? So, you can actually prove that this is a superposition of 2 peaks from the 101 and 110 peaks of the tetragonal crystal. The machine that we have for teaching does not have the resolution to separate these peaks out. Okay? And that's why the peak is asymmetrical. There's absolutely no reason why these peaks should not be symmetrical if they represent a single peak. Now, I haven't taught you this, but one reason why the peak is so broad is because the barium titanate is there as a powder. Okay? That means the crystals are very small. The smaller that you make the crystals, the less the Bragg law is properly satisfied. Okay? Whereas the lithium fluoride was a large single crystal. But I haven't taught you that. Okay, so I think we've addressed everything about the practical and the feedback. And if you have any questions, just ask.
With the size of the crystal being relevant, I presume that's due to the number of planes within the crystal. It's due to the number of planes present within the crystal.
In the powder, you mean? No, the planes are exactly the same, but the Bragg law is only satisfied properly if the crystal is deep. And as soon as you make it smaller and smaller, you will get wider and wider this diffraction angle. And the other reason which we have covered actually is strain present inside the crystal. But I have no evidence that the barium titanate has strain. Okay, well, we have actually finished, so we can stop now, okay? If you have no more questions. Everyone happy? Okay.
Yeah.
So obviously I'm going to pick up these manuscripts and we'll see when the others can select your manuscripts. Yeah?